Professor Otto von Koert from the Seoul National University. His title is Torsion Flow, an analog of the Ricci Flow for contact manifold. Well, it's an there's an interrogation point. An analog of the Ricci Flow for contact manifolds.
Yeah. Okay, thank you for the invitation. And yeah, it's great to be here again with nice weather. Not too hot, unlike Seoul, actually. So this time I'm going to give a talk about a topic I usually don't talk about, just to kind of vary the usual restricted free body problem or variation of this. I've written down my collaborators, Xiucheng Zhang, Jiwei Chen, and Jintong Wu, and I got a lot of help from Jixin Cheng. And okay, so what's the goal of this talk? So I'll be honest. The goal is a mostly unsuccessful attempt well, okay, I put this between brackets to not emphasize it too much, to define a Ricci type flow for contact manifolds. Yeah, actually for CR manifolds, but we'll see what they are. So why do you want to do that? Well, that part is easy to answer. If you have a contact manifold, maybe you want to improve qualities, so actually it will be a flow for a pair, contact form and complex structure, and it will try to improve, in some sense, the complex structure. So you could say, yeah, that sounds nice, so why not? So how do you come up with this flow? For this, I'm going to survey the Ricci flow, where things do work. And yeah, I'll kind of describe how you get to this flow, and then I'll point out what the problem is with this flow. Okay, so we call the Ricci flow, or maybe not recall if you haven't seen this, but okay. So my manifold Mn, and N will be at least 3, and usually it will be just 3. So, okay, so what do we do? So we consider the so-called Einstein-Hilbert functional, which takes a metric and sends it to this integral over the scalar curvature. Okay, so this is the scalar curvature. And yeah, well, if you have followed the course in general relativity, you know that critical points of this functional are Einstein metrics. Okay, and so now what's the idea? So maybe I should point out this is Hamilton. The idea is to kind of take the gradient of this functional epsilon, and this gives you a flow. And Hamilton was very brave. He just wrote down this flow. So Hamilton take the gradient. So yeah, I just remember this was a conference on conservative dynamics. So this flow will definitely not be conservative. It will also not have so much to do with symplectic. But yeah, it's a flow. So take the gradient flow. So what does this gradient flow look like? Well, you can compute it. So for a family, I'll write down the flow. Then I will tell you this flow cannot possibly work. Then you modify it, and this modified flow will actually preserve the volume. And then you modify it further such that it does not preserve the volume. So answer is yes and no. Okay, so for family of metrics, GT. So the derivative will be 2 divided by n times the scalar curvature of this metric times the metric minus 2 times the Ricci curvature. Okay, and let's call this term 1, and this term with the minus sign, let's call it 2. And then, so Hamilton observes the following. So 1, okay, so this is a PDE, and does not look very pleasant. So what can you do with it? Well, you can linearize. So if you linearize this, then you will see that one behaves roughly like a backward heat flow. Well, actually with an additional problem, but I will not go into that. And 2 is like a forward heat flow. So I put it between quotation marks because, well, when you do heat flow, well, the right-hand side, the linearization should be elliptic operator, but it has a big kernel due to the diffeomorphism group, so, but with kernel. And this gives some extra trouble. Not sure this is very clear, but okay. Okay, so 1 is really a bad guy. If you have 1, you don't get any short time existence. So we need to get rid of 1. So no short time existence if you include 1. So the idea is now to, instead of taking the scalar curvature, you take the average of the scalar curvature. And then you get a new flow, and this new flow will be the kind of normalized Ricci flow, which preserves the volume. And this is a computation which I will not carry out. So where am I? Yes. So modify. So the new candidate will be the following. And this is the average. So it's just, so R equals okay, so this is M. Okay. And okay. And then, well, this is kind of annoying to work with this nasty looking integral. So most of the paper of Hamilton is then studying this flow. So this is the unnormalized Ricci flow. And then, yeah, maybe I should say, okay, you can then prove short time, more precisely, Hamilton can prove short time existence because it's a kind of involved thing. Okay. Huh? It's just a fixed point, yeah. Then you're just rescaling depending on whether you have positive or negative curvature. So if you have a sphere, it will in the unnormalized flow, it will just shrink. And if it's hyperbolic, it will just expand. And yeah, if you're somewhere in between, then some directions will contract and others will expand. Right. So let's say this. So theorem, Hamilton, Ricci flow in both forms has short time existence. And of course, there's much more. But let's not talk about that. Okay, so this is the starting point I want to take, because now I want to switch to the contact world and then say, okay, how do you adapt this to the contact world? So if you go back, so we needed this functional here. So we need an analog of that. So now I'm going to spend like, I guess, almost half an hour how to define the analog of that for contact manifolds. Okay. So try to mimic. Okay. So I'll spend a lot of time talking about CR manifolds, and then at the end I'll switch to some situation which are actually just contact manifolds. But there are some notions which we will need, so I need to go through everything. Okay, so what's CR geometry? Yeah, so let's just write down the definition. So a CR structure, Cauchy-Riemann structure, but it's always written as CR on M consists of the following data. So we need a distribution in the tangent bundle. So we need a complex structure on the, or almost, a complex structure on this distribution, which we usually extend to be 0 on the complement. And there's one more condition. This needs to be integrable. So there are many ways to put this. So this is the shortest version I know. So if you take two vector fields or two sections of this distribution and you take the Lie bracket, we want it to land again here. And what does this D10 mean? Well, it's just the complex linear part. Of D tensor C. Okay, so well, if you take D tensor C, you can diagonalize the J into an I, well, plus I eigenvalues for plus I and for I minus I, and this is then for plus I. Okay. Great. So okay, basic examples. So I'll give two examples. The first example is stupid example, but it should be pointed out. M is a complex manifold. So then you just take D everything, and then there's nothing more to say. But this is not the case we will consider. We will take usually a hypersurface inside a complex manifold. Okay. So this probably sounds familiar from, well, actually from Miguel's talk, right? I mean, you, when you talked about the link of a singularity, you defined the context structure precisely in this way. Now here, this distribution doesn't have to be a context structure, but it smells already like it could be related, and it is, of course. So in principle, with this definition, this distribution can have any codimension, but we will now restrict to codimension 1, and we will assume that this is just the kernel of some one form. And I will call this one form theta, so not alpha. And okay. So then, well, what we are going to do is we are going to define the so-called Levy form. And so what is this? This is a bilinear form, and it looks like this. One zero. Okay, so this is the Levy form. And, well, this thing can have all sorts of behavior. It could be 0, or it could be all kinds of things. But we will look at a case where this is where this H is a metric. So, and this is known as strict. This is known as a strictly pseudo-convex CR structure. So, consider strictly pseudo-convex CR structures, well, of codimension 1. So this means that this H defines a Hermitian metric. Okay. Right. Okay, so now, okay, the relation with contact. So, so strictly, okay, so this pseudo I will abbreviate by this letter psi. Strictly pseudo-convex CR always implies that you're contact if in the setup. So implies the contact structure. And so this is always true. So now you can ask, suppose I have a contact structure, I can always choose a J, right? So do I get then a CR structure? And so this implication is true in dimension 3. So, okay, so you would say, how do you do it? Just choose an almost complex structure in your complex structure for on the planes, and you're done. But it's not true in general. Not in general. What's the problem? Because this CR, well, it's still here, this CR structure needs this integrability condition, which is automatically satisfied if your symplectic vector bundle is actually a complex line bundle, because then it's just one-dimensional, so nothing can happen. But it will fail in general. So this is not in general. So, okay. So this does not hold in general. This is always very confusing when you talk to CR geometry people, but maybe in this audience this is not a problem. Okay, so now, so central questions in CR geometry, they're actually mostly solved nowadays, but okay. There will be familiar sounding questions, again, kind of mimicking Miguel's questions from Monday. So we call closed CR manifolds, okay, so I need to write the alphabet. Call it fillable. Okay, so what sounds like a reasonable definition of fillable? Well, if there's a complex manifold who bounds this guy, such that the complex structure induces the CR structure. So So, great. So you can kind of feel the familiar question, what does the boundary know about the interior? But there's a kind of, so I should point out this is different from symplectic fittability. It sounds so similar. But in CR geometry, the thing you care about is, well, in contact geometry, you only care about the contact planes. And in CR geometry, you also don't care about this form, but you care about the complex structure. And so it's a much more geometric thing than the contact topological version. So here's another definition. So we call it embeddable, which is actually the stronger notion. If there's an embedding into Cn, where n may be very big, such that the pullback of the standard complex structure induces this CR structure. Okay, and so then there's a theorem by Boto de Monvel, and this says that if you have a CR structure, CR manifold, so closed CR manifold, and the dimension is at least 5, then it is embeddable. And so this, I think it is a bit misleading because the integrability condition in CR structure is really, really restricting things. And so if you try to translate this into symplectic geometry, it will mismatch your expectations. Okay, so here's an example where it is what is kind of funny. But in dimension 3, it's false. So what's the problem? So I will just give an example. So they're known as the Rossi examples. And I will describe it in a somewhat contact geometric way. So let's look at S3, at standard S3 in C2. And so it's just a standard round 3 sphere. And okay, so we can look at the contact structure. So what's the contact structure? So D is kernel theta. So let's say theta. So okay, so f is this strictly plurisorpharmonic function, but we can just write it down in a formula. So it's I over 2, then z dz bar minus z bar dz, and then probably I should put some coordinates. Okay, but for S3 we have a global trivialization of the contact structure using quaternions. So let's use this. Okay. So does this make sense? So the rape field would be I times Z, and then J times Z is one orthogonal direction, which lies in the contact structure, and K times Z is another one. And then you could say, well, the standard complex structure, so let's call it J0. J0 for D, for this distribution, is just okay, so it's just this matrix. So since, let's call this U and this V, U to V and V to minus U. Okay, so that's what the standard complex structure does. So now I'm going to deform it, and it looks for any contact geometer like a completely harmless deformation, but this turns out to be very bad for CR geometers. So deform. Okay, so we just deform it with the parameter t. And so kind of for t very small, it looks like it's almost the same. But this guy is now not embeddable. Okay. Yes. Yes. Yes, so a CR manifold has this data, distribution, and complex structure on the distribution. And, okay, so we are looking at hyperplanes anyway, so let's just consider that. So then you can ask, so if I have a complex manifold and a hypersurface in this complex manifold, then I can ask if D is defined as the intersection of these two guys, so does I kind of induce the given J? So does that make sense to you? Yes, yes, of course. But yeah, okay. So now the point is, it usually does not happen. So if you even do this, which looks pretty harmless, it will not work. So this is. Yeah. So it's really kind of, you want to kind of induce the complex structure on your distribution. So yeah, in symplectic geometry, you just induce the symplectic structure, but now we are asking for something different, and it's much more geometric, so it usually does not work. Well, except you have, of course, this theorem here. Okay, so this is not available in CR sense. Yeah. Yeah, so you look at, so it is a very ad hoc construction. So you look at, so you can look at, holomorphic functions. So they're called usually CR functions. So they're holomorphic with respect to the structure. And then so what you play a game. So you first look at RP3, and you try this guy, and then you get holomorphic functions. But for T0, they satisfy some kind of symmetry property. But for T bigger than 0, they don't. So they will never descend to a well-defined CR function on S3. So it's a bit of an ad hoc construction. So it's very geometric. it's very different from symplectic geometry.
Like, how would you show you can't put it in C11?
Yes, so there's a general theorem that tells you fillable implies, sorry, the other way around. Embeddable implies fillable. Sorry, I got my implications wrong. Not sure I show this now. Sorry, I cannot answer right now. Okay. I know, but it's a good question. I just don't remember the reason. So for the fillability, you use the CR functions, and then you, okay, then I don't remember. So. Okay, so now let's look at. So now I'm going to define a kind of preferred connection on a contact manifold, actually on a CR manifold, but it's also on a contact manifold. So now we'll be more specific. So we look now at this theta contact form, and we take this. Well, let's call it the CR structure, but you can just call it a compatible complex structure. And I will denote the Rape field by T. And so the reason to do so is that I will also use scalar curvature, and then it becomes a huge mess. So in this CR business, people denote the Rape field by Xi, but I don't want to torment you with that. Okay, so you take this kind of intermediate thing. So now we get a metric. Okay, so this is very familiar. So just a standard metric. And then we get, of course, you get the Leibniz-Vita connection. But we are going not to use the Leibniz-Vita connection. We're going to use a different connection. And what motivates the other connection? Well, we also have a Hermitian metric. So the Hermitian metric is just, let's call it H, on V. And it's given by, well, you can guess. Okay, so here's our Hermitian metric. And so if you have a Hermitian metric on a holomorphic vector bundle, you have this Chern connection. And now you try to build a kind of mix of this Leibniz-Vita and Chern connection. So I will just give some kind of theorem that tells you there's a connection that has some nice properties. There's a formula relating this to the Leibniz-Vita connection, but it's not a very pleasant formula, so I will not write down this formula. So this is a proposition / definition. So there's a unique connection, and we will call it the Tanaka-Webster connection. Such that, okay, so what do we want? So this will not be the Leibniz-Vita connection. So it will preserve the distribution. It keeps J parallel, and it is also metric. It also has satisfies metric compatibility. So that sounds very good. But it sounds so good that there must be some catch. And the catch is this thing has torsion in general. So the torsion, but the torsion has some kind of decent properties. So the torsion is 0 for all complex linear vector fields. And for if you have a pair, complex linear and complex antilinear vector fields, then you have a nice formula for the torsion. Okay, and then finally, right. And where this tau is the so-called pseudo-Hermitian torsion. And so what is it? So it's just given by this formula. So you use this because somehow it catches the essential part of the torsion. The rest is somehow you already know. So this. Okay, so what is essential is, of course, kind of an opinion, so I put it between quotation marks. Okay, great. Yes. So, what do you mean? Can you say it again? Yes. Yes. Sorry. So this is. Sorry. Yeah. You could say Z in D10 and W bar in the other one. H is this Levy form. Yeah, so it's just d theta and then, well. Okay. So far, so good. Okay, so what is this pseudo-Hermitian torsion? Because torsion is kind of unfamiliar to most people, I guess. I mean, it was certainly unfamiliar to me. But there is a lemma which tells you what torsion is. And you prove it just by computation. But I think this is very helpful to know. So the torsion is equal to the following. It's minus a half times J times the derivative of the Lie derivative of J in the direction of the Rape field. So in other words, tau is 0 if and only if J is invariant under the Rape flow. So now you can wonder, how special is this, kind of having a J which is invariant under the Rape flow? And of course it's very special. So having a J that is invariant under the Rape flow means that this manifold, this contact manifold, together with the complex structure, is so it's known as K contact. Let me say the proof is almost shorter than the statement, but I will write out the proof. So then I will also explain what this means. And secondly, so K contact means actually that there is a perturbation, let's say tau tilde, such that tau tilde has periodic Rape flow. Okay, so essentially these torsion zero things, they're always contactomorphic to some pre-quantization bundle, maybe over an orbifold. So they're extremely special. Okay, so how does this go? So this is, so this you can find this in a paper of Chern and Hamilton, and in an appendix which is due to Weinstein, but he claims that it's already due to other people. So okay, let's go through the arguments. So okay, I promised the proof of one is shorter than the statement. So let's see, what did I write here? I cannot read this. Right. If J is invariant under the Rape flow, the contact form is already invariant under the Rape flow, so D of the contact form is invariant under the Rape flow, so this metric is invariant under the Rape flow. And this is precisely the definition of K contact. Because this just means Rape T is killing vector field. Okay, so something is called K contact if the associated Rape vector field is a killing vector field. Yeah, everywhere. Yeah. I mean, if it's somewhere 0, then it means nothing. Yeah. Okay, so for 2, so why does K contact mean that you actually can perturb to periodic rate flow? So this is I think it's a nice argument, so I just give it. Okay, right. So we need the following fact. So, okay. So, of course, this is compact. Because if it's not compact, I cannot do this. It's not true. So the isometry group of a compact Riemannian manifold is a compact Lie group. So, and now we have this one-parameter family of isometries generated by the rate flow. So the flow of T defines one-parameter subgroup. So the closure is actually a torus. And so now if you're on a torus, you're going in some direction, which is maybe not periodic, but you just perturb slightly until you're periodic. Okay. So you need the compactness, of course, for this. Okay, so you just perturb until you get periodic rate flow. So you just get a contact vector field, and then this contact vector field is transverse, so it's also the rate vector field of something, and this gives you this perturbed thing. Okay, great. So now we have this. And then there's another fact. So this kind of emphasizes how special this distortion zero, identically zero is. So if the dimension of the contact manifold is 3, which is the case we will be looking at, and the torsion is 0 everywhere, then actually M is known as Sasaki, which basically means that the symplectization, so this is the symplectization, is Kähler. Okay, so in other words, if we have torsion 0, we have a very nice complex structure on the symplectization, so maybe this helps a lot to write down holomorphic curves. So then you could be happy. Okay, so we need one more ingredient to define the torsion flow. Okay. Namely the curvature. Okay, so now there are two ways out. So there's a kind of intrinsic way to define this, and there's a kind of ad hoc formula which is shorter and probably easier to understand. So how quickly do you want to have lunch and go hiking? This is the main issue. You don't care? Okay, then you'll get the kind of longer version. You can still stop me. No? Okay, then not. Okay, so the curvature you can define via the structure equations. So use structure equations. So we are going to need a moving frame. So take frame, say T, Z alpha, Z beta bar for the complexified tangent bundle. Okay, and then we have a dual frame, so the co-frame, and this is theta, sometimes called theta 0, and then theta alpha, and then theta beta bar. Okay, so it's just a dual frame. Okay, okay, so then you can write down the connection form, and if you take the derivative of the connection form, okay, so okay, let's write it like this. Okay, now I'm going to write down well, not the entire alphabet, but a long formula. Okay, so you can compute that that the curvature form will look like this. So this is like a Riemann tensor. But of course, it's in a different setting because everything is complexified. And there are two other terms which are related to the torsion. Now this is a covariant derivative. Right. Okay. So this is like analog of Riemann tensor. And then you contract two indices to get the kind of the pseudo-Hermitian Ricci tensor. And from there you contract again to get the scalar curvature. So we get a pseudo-Hermitian Ricci curvature. Okay, I'll indicate it with a star to, to indicate that it belongs to this funny connection, to the Tanaka-Webster connection. And it's just, you just contract. Okay, so this is, probably this should be here, yeah. And then again, so to get the Webster scalar curvature, just put, we contract again. Okay, so this is the kind of intrinsic version. Well, it uses frames, but it's well defined. Now, okay, so how can you think about this? Well, one way to think about this is to actually use the Levi-Civita connection for this metric. And then we have an alternative formula for this Webster scalar curvature, which tells you somehow what it is. So what does it mean? So here's an alternative formula, which is maybe more telling. Okay, so it's the scalar curvature. You forget about the rape directions, and then you add some constant. Okay, and then there's some numerical factor. So it's kind of the part of the scalar curvature. In the, well, just in the distributions if you want. Okay? Yes. So in some sense, this Webster's curvature forgets, well, I mean, you are actually, so when you do this, yeah, maybe I was not very clear when you do the summation, you only look at the directions inside the context structure. So it's somehow blind what happens transfers to this. And this is somehow, so what you see here, you just subtract this part. Yeah, keep also in mind the rape vector field is orthogonal to the context structure with this metric. Okay, so, and this is the scalar curvature we need to get an analog of the of this Einstein-Hilbert functional. So now, so we just take a complex structure and a contact form, and we send it to this Webster curvature, and it depends, of course, on the J and the contact form. And, well, we need a volume form, but this is easy. So, okay, so let's just do the dimension. So let's say dimension 3. Otherwise, you just raise this to some power. Okay. And, okay, so then maybe theorem. So this was already done by Chern and Hamilton. So critical points of this functional are, these K contact manifolds. Okay, and so now we want to do kind of gradient flow for this thing, and I will look at a gradient-like flow, and yeah, so far so good, but now, let's start with the good news, but this is not so good news, and then we give the bad news. So So we try, so this is actually a fairly motivated try. So I call this the torsion flow. So this is a gradient, so you can just do a computation. This is a gradient like, well, okay, I put it flow for E. Okay. So okay, so clearly well, if you're arcane contact manifold, then this is 0. So then you're just rescaling your contact form. If you normalize volume, then you're just doing nothing. Okay, great. So now, so first the good news, but it's not so. It's just so on simple CR3 manifolds. So what does this mean? So this means coming from Lie group, for example. So if you have a Lie group, then you can define your contact structure and CR structure in a very simple way. You just define it in one point, and then you use the Lie group action to define it everywhere. Okay, so you get some kind of invariant CR structure. Okay, so on these simple contact manifolds or CR manifolds, this flow behaves as expected. So for example, if you take these Rossi examples and you take some deformation, it actually flows to the standard structure. Okay, now I can say a bit more. So if you take a complex structure on a torus, so let's take the standard context structure on a torus, and take some kind of J which fits, some global trivialization or something of the context structure, then what will happen is it will just kind of, it will skew the complex structure. So one direction gets kind of contracted and the other expands. Okay, so this sounds familiar. So now the bad news, and maybe this is the most useful part of this talk. So the bad news is, so the linearization in general of this equation, so is not of heat type for not even of weak heat type for general initial conditions. So that means for general initial conditions, I don't have short time existence, so then it's kind of useless. Now you can say, okay, let's look at more special initial conditions. Maybe we can do something. Yes, so, but, okay, so no short time existence. And now, okay, so what can you do about this? Okay, so you can cheat. So one way of cheating is, well, it's a proof, but it's kind of silly. You can restrict yourself to analytic initial conditions, and then, well, you have short time existence, but for silly reasons. So that's not useful. So remark, not useful. Analytic, real analytic. And then there's a kind of, well, let's call it a theorem, but I'm not really sure about this. It's certainly in progress. So if M3D theta j is embeddable, then embeddable. Short time existence. So let me briefly say what the idea is. So when you're embeddable, then you can write out the linearization, and it looks then it's, well, modulo some kernel, it's of heat type. But this embeddability without kind of further work is actually not preserved under this flow. So then you apply some coordinate transformation to move it kind of back in the right direction. So you modify this flow to kind of make it work, but I'm not sure we didn't make any mistakes. So, so the kind of, if you really want to do it, there will be lots and lots of computations looking at the linearization of this guy. And so the problem is that this guy, when you start to linearize it, you get lots of derivatives of distortion and Webster curvature, and they don't review what they want. They don't review whether they want to be positive or negative, so it's very hard to decide what's happened. So this claim that it's actually, even this claim here, you need to look at examples, because you just look at the general term, you have no idea whether this is positive or negative. Okay, so to conclude, I recommend you to stay away from this topic, because it's, yeah, it's kind of complicated. And if you look at the kind of the literature, so this was actually, some versions of this flow were suggested in the paper of Chern and Hamilton, and then later on the other versions. So you can, so if you're a contact geometer, maybe if you're interested in dynamics, this flow looks kind of somewhat attractive because it just modifies the complex structure. But then when you start to work with this, it behaves so terribly that maybe it's best to stay away from this. So, okay, so that's my conclusion for this talk. I recommend you to stay away from this unless you really want to work with heat flows and kind of do a lot of analysis. Okay, thank you for your attention.
So, any question or comment?
Yes.